Good evening. Thanks for listening to this presentation. We are Curtin University postgraduate students, and we are going to present our work for the development of 3 different agents for the reinforcement learning course. Our agents are in 3 different environments. The environments are the swimmer, blackjack, and kung fu master. My name is Patricio Alvis Rojas. I'm also with Reuben, Woon, and Qingqing. To begin with, this presentation does a complete summarization of the development and the evaluation of 3 reinforcement learning agents, implemented and extended from the course practicals, across 3 different environments, which are the swimmer from Mujo Co. and blackjack and kung fu master from Atari. Each agent represents a different challenge, from continuous control in the case of the swimmer to strategic decision-making in the case of blackjack, and finally, a high-dimensional visual input in kung fu master. So this presentation will briefly cover the different environments, the main implementation details, the training challenges we had, and the key results, highlighting how the different algorithmic differences affect learning dynamics and overall performance. So to begin with, the first environment is the swimmer from Mujo Co.
For this environment, the problem to be solved is training 3 agents to control a swimmer that consists of 3 links and 2 rotors. The state of swimmer is continuous, which consists of 8 elements. 3 angular position of the robot's body parts, front tips, first rotors and second rotors. Other 5 elements represent their velocity, including the tip's velocity along the x and y axis and the angular velocity of all 3 parts. The action of the swimmer is continuous, range from -1 to 1. It is twice applied by 2 rotors. The reward equal to forward reward minus the control cost. Forward rewards give a positive reward for forward movement, while control cost penalize the large action with a negative reward. Then the goal of the swimmer is applying torque to the rotors and using fluid friction to move as fast as possible. First agent is linear SASA. Linear SASA is an unpolicy TD control method that's using linear function approximation, as shown in the slides. It estimates the action value function with the set of feature and the related weight. The algorithm applies the SASA targets for bootstrapping and computes the TD arrow to get learning. Then the parameters are updated through gradient descent based on that arrow. The modification of linear SASA first use the tail coding feature for swimmer's continuous state and add discretize the action wraps, so linear SASA can operate in continuous space. Then employee eligibility traces SASA with replacing traces to improve assessment by improve daily reward credit assessment by passing TD error across time steps. Also use quantile-based data-driven bounds for tail coding, which makes the feature more accurate. Finally, wrapped angle feature to the range from -pi to pi to maintain feature continuity. Second agent is Reforce. Reforce is a Monte Carlo policy grading method that directly learn to maximize the expected return. As shown on the slides, it estimates how good each action is by looking at the total feature reward is bringing and adjust the policy in the direction. To make training more stable, we introduce a baseline. This helps reduce the variance of gradients without changing its direction. The modification of reference. First, add value baseline and advantage function to reduce high variance. Second, apply the batch normalization to the advantage for more stable update. Third, introduce entropy regularization to keep the policy exploring and prevent early collapse. Also use reward shipping to reward forward movement and penalize high torque. Finally, employ the diagonal Gaussian policy with log variance clipping to improve numeric stable. The next agent is actor critic. Actor critic method represent re, sorry actor critic combines the idea of both value-based and policy-based reinforcement learning. As shown on the slide, it keeps two sets of parameter: the actor which update the policy and the critic which learn a value function to evaluate the policy. The modification of actor critic. First, adopt a continual policy with 10 Gaussian to make the model better at handle swimmers' most continuous action. Second, replace the simple one-step TD target with an n-step return, which give more accurate learning best for reading critical credit over multiple steps. Furthermore, entropy bonus to encourage policy exploration and add a value loss coefficient to keep a good balance between learning. In the end, use gradient clipping and a linear learning rate decay with help make the training process more stable. Here, the three graphs above show results from the original experiment. Down below are the improved version. Sasa is more stable and gets high reward. When reinforce is used the continual action, the learning effect improve significantly, and the continual version is actor critics. Actor critic performs the best. It's both stable and quickly achieve high reward.
So the second environment is Blackjack in Atari. The ALE Blackjack V5 environment is set up in the following way. The state space is a grayscale 210 by 160 pixel frame, which are downsized to 84 by 84 during processing. There's also the dealer and player's hands and the game dealer's deck. The action space are two actions, to hit and to stand. The reward signal is +1 for a win, +0.5 for a blackjack, -0.5 for a loss, and -1.0 for a bust. This reward signal is not native to the environment. It was hand-defined. The original reward from the environment is always -200 when the player loses the game. This reward that was handcrafted is laid out in this manner to encourage the agent to carefully learn the importance of his actions, which is why winning and busting have heavier reward weights than getting a blackjack or losing conservatively. The overall goal of the environment of the agents is to guide the agents towards learning an optimal policy for when to hit or stand to maximize its expected episodic return. This is achieved by reinforcing winning outcomes and discouraging losses through reward feedback, enabling the agent to improve its decision-making over successive blackjack hands. The shared environmental changes for these agents are utilizing a custom blackjack reward wrapper to translate the ALE's frame-based output into structured rewards and detect outcomes such as win, losing, or busting by template matching. Introducing an execute macro action to combine the low-level Atari key actions, such as up and fire for hit, into discrete macro actions, which create a higher level control abstraction consistent across all the agents. We've added a prepare state function to crop, resize, and normalize grayscale images from 210 by 160 pixels to 84 by 84 pixels. We've replaced the environment numeric reward signals with visual OCR style detection for more deterministic game end feedback. We've also inserted no-op loops for frame stabilization after macro actions, ensuring consistent frame transition frames and gameplay. The first agent is dueling DDQN, which combines two main improvements to the usual DeepQ network, a dueling architecture and a double DQN update. A replay buffer enables stable learning by sampling past transitions, whilst epsilon greedy exploration ensures a balance between exploration and exploitation. The target network is periodically synchronized with the online network to stabilize learning. My improved agent uses the following improvements over the default agent. We move from an MLP to CNN feature extraction, which enables spatial reasoning from visual frames. We use a convolutional feature extractor with a +2 stream value advantage structure, which dynamically computes the flattened size. We use a large replay capacity, which trains every 4 steps. We use progressive episode-wise epsilon decay, which decays from 1.0 to 0.05. We use a more robust episode termination detection, which uses terminated or truncated, as well as detecting the outcomes through the wrapper. We use state pre-processing for ensuring consistent inputs into the CNN, which allow for faster learning. The second agent is an actor critic agent, which follows the A2C, formula. The actor critic actor, the policy network, updates its behavior directly using gradients of the expected return, while the critic, the value network, estimates state values to reduce the variance in policy updates. This allows the agent to learn both what to do and how good it is in each state simultaneously. The reward agent uses the following improvements over the default agent. We've replaced MLPs with convolutional CNN architectures for both actor and critic networks, enabling spatial pattern recognition for visual game frames. We use a shared convolutional encoder design, which are 3 convolutional layers plus ReLU activations, with separate fully connected heads for policy and value estimation. We added entropy regularization to maintain exploration, which is weighted by entropy beta, and progressively reduced it per episode to encourage exploitation in later training. We've also simplified the policy selection process to always use greedy argmax actions at inference for stable evaluation. The SAS agent is an on-policy temporal difference method that learns action values by updating the current state action pair to the next state action pair. It follows the same policy for both acting and learning, meaning exploration directly influences updates. My improved SAS implementation uses the following enhancements over the practicals baseline. We replaced the tabular tile-coded linear approximator with a deep convolutional Q network, enabling end-to-end with deep convolutional Q network. We've replaced the analytical updates with back propagation through differentiable Q network trained by Atom Optimizer. And we implemented an optional per hand update mechanism to learn only after complete hand outcomes, improving stability in this particular environment. Next, please. These are the agent performance comparisons. On the top, we've got the practicals implementations and the improved agents on the bottom. It should be noted that due to how the environments are implemented, I've had to utilize the hyperparameters from the practicals and whilst using my architecture from the improved agents to be able to perform this comparison. As you can see, all the agents don't typically show any improvement in its learning. Most of its performance is relatively stable. The rewards, it should be noted that the rewards are capped roughly around 0, which is expected, as the terminal condition for the environment is the player losing the game, with no workaround or other terminal or terminated condition. The Archicritics agent clearly performed the best out of the agents tested because the agent fit the problem better as its on-policy updates and direct policy optimization handled the sparse, delayed rewards more effectively than the value-based methods. Its simpler critic target and continuous learning each step led to a more stable and consistent improvement than the delayed or noisy updates in the DED-QN or SAS agents.
Well, finally, the third environment is Atari Kung Fu Master. So as we did before in the other Atari environment, we also did the same modification where we had to transform the environment. So Kung Fu Master, it's a 2D platform game. It only brings positive rewards by defeating enemies. And every episode finishes when the Kung Fu Master loses the 3 different lives. So there are 6 basic actions, which is basically moving and jumping and going down and punching. And the total combination brings a total of 14 actions, but in practical terms, there are only 6 that are used. So the environment uses 210 and 160 pixels composed by 3 different channels in RGB. So as I said before, we had to transform the environment just as we did before in Blackjack, doing the same changes, but also in the end, we normalized the images to make the environment faster. And the challenges of this environment are because the enemies are coming from both sides, but that only starts when the rewards are higher. So the environment is dynamic, it changes. The other thing is the environment is partial observably because the enemies can appear suddenly from any side. Also, the rewards are delayed because you don't receive any reward while you punch. You need to kill the enemy to get those rewards, so there's a bit of a delay. And also, it requires a good balance between exploration and exploitation. So the first agent is DQN. At the right side of the screen, you can see how the agent plays. So this agent uses a deep Q network, a neural network that maps each gate state to an estimated Q value for all possible actions. It follows the standard architecture from the practicals. It's fully connected layers with ReLU activation, MSC loss, and Alarm optimizer. So the target network is synchronized every 3,000 steps to stabilize learning. It also includes the replay and policy. It reduces the correlation between the experiences and transitions because these are stored in a replay buffer and sampled uniformly. Also, I implemented a epsilon greedy policy that starts going down with an epsilon decay. So additionally, in the beginning, there is a warm-up for the buffer to begin the learning. Only when the buffer is full of information. The second model is the deep SARSA. As you can see in the video on the right, this agent is a little bit more conservative. It doesn't spam punches as the DQN one. It thinks more about the future and what's about to happen, about the next action, just as you can expect from SARSA. So deep SARSA uses the same Q network we used before, but it uses the SARSA mathematical formula to implement the different changes. So compared to the DQN agent, Deep SARSA plays much more in control. And finally, the last agent is the actor critic agent. This is based on the actor critic framework. It has a policy head and a value head. They are both separated, but they share the body of the information that is used for learning. So it uses a TD with n steps to ensure that the information is processed in the better way. So the policy becomes stochastic early on, as you can see on the video. So as the fighter is not penalized for attacking, you can see that it also spam punches. So the results are the following. On DQN, in the beginning, the agent was learning, but it reached the top in a really quick way, while when we implement epsilon decay and we let the agent learn for around 400 episodes, it improves a lot and it reaches a really high ceiling. On the case of Deep SARSA, the agent wasn't learning at all in the beginning, but once the agent is tuned, it constantly learns, but is much more stable than DQN. And in the last case, the agent critic wasn't learning much from the environment until we tune it with the TD and it started to learn. And the difference is that this one learns so much quicker than the DQN and that the expected Deep SARSA agents. So in conclusions, there are 3 different agents. Each one had different challenges. For instance, in the swimmer, it has been demonstrated stable continuous controls on once reward scaling and gradient clippings were tuned. The learning was required precise balance between exploration noise and policy updates to avoid oscillations. In the case of blackjack, it reached fast convergence through tabular simplicity and low stochasticity. The exploration had limited impact, showing that policy evaluation accuracy was more critical than exploration strategy. And finally, in the Kung Fu Master, it was exposed the limitation of an actor-critic architectures under high-dimensional visual inputs. Its performance improved only with a strong entropy regularization and a stable gradient control. It was extremely necessary to make the agent explore. So in overall, each environment emphasizes a different learning challenge: control precision, strategic decision-making, and visual generalization, highlighting the need for environment-specific algorithm design and careful hyperparameter tuning. Thank you very much.